There are places in the universe that light will never reach. Not because light is slow, it's the fastest thing that exists, but because the universe is doing something that breaks all the rules. The fastest thing in the universe is losing a race against space itself. You're about to discover why. Are you ready for this journey? Let's begin. Let me take you back to the beginning, not your beginning or even Earth's beginning, but the beginning of everything. 13.8 billion years ago, the universe burst into existence. In the first fraction of a second, it was smaller than an atom. Then, in a period called cosmic inflation, it exploded outward faster than you can blink. Space itself stretched and expanded, carrying energy and matter along with it. This wasn't an explosion in space, it was an explosion of space. And here's the critical part. That expansion never stopped. Right now, at this very moment, the universe is still growing. Every second, the fabric of space stretches a little more, pushing galaxies farther and farther apart. Now you might be thinking, okay, the universe is expanding, so what? Light is fast. Can't it just keep up? That's a reasonable thought. After all, light travels at about 299,792,458 meters per second in a vacuum. In 1 year, a single photon covers roughly 5.88 trillion miles. We call that distance a light year. It sounds incredibly fast, and it is, but the universe doesn't play by the rules you might expect. Here's where things get strange. When we look out into space, we're also looking back in time. The light from the sun takes about 8 minutes and 20 seconds to reach your eyes. That means when you see the sun, you're not seeing it as it is right now, you're seeing it as it was 8 minutes ago. The farther away something is, the older the light we receive from it. When you look at the Andromeda galaxy, you're seeing light that left there 2.5 million years ago. When the James Webb Space Telescope peers into the deep universe, it's capturing photons that have been traveling for over 13 billion years. Those photons began their journey when the universe was just a baby, less than 300 million years old. In fact, in January of 2026, astronomers confirmed that the James Webb Space Telescope had spotted the most distant galaxy ever observed, a galaxy called MOEMZ14. The light we see from MOEMZ14 left that galaxy only 280 million years after the Big Bang. Think about that. We're seeing this galaxy as it appeared more than 13 billion years ago. Back then, the universe was still in its infancy, stars were just beginning to form, and the cosmic landscape looked nothing like it does today. But here's the catch. Even though we can see MOEMZ14, that doesn't mean we could ever reach it. In fact, we can't. Not even close. And it's not because we don't have fast enough rockets. It's because the universe itself is working against us. You see, space is expanding everywhere, all at once. It's not that galaxies are flying through space away from each other like rockets. It's that the space between galaxies is stretching. Imagine you're an ant walking on the surface of a balloon. As someone blows up the balloon, the rubber stretches, and every point on the surface moves away from every other point. You're not moving. The surface itself is expanding. That's what's happening in the universe. And the farther apart two points are, the faster the space between them grows. This expansion is measured by something called the Hubble constant. Right now, astronomers estimate that for every 3.3 million light-years of distance, space expands by about 46 miles per second. That might not sound like much, but when you're talking about distances across billions of light-years, it adds up incredibly fast. Let's do some math together. Imagine a galaxy that's 10 billion light-years away from us. For every 3.3 million light-years, space expands by 46 miles per second. So across 10 billion light-years, how fast is that galaxy moving away from us due to the expansion of space? The answer is staggering. It's receding at hundreds of thousands of miles per second, far faster than the speed of light. Wait a minute, didn't I just say that nothing can move faster than light? Here's the brilliant part. That rule still holds. Nothing can move through space faster than light. But space itself isn't bound by that rule. Space can expand as fast as it wants. There's no speed limit on the stretching of the universe. So while no object can zip past you faster than light, the expansion of space can carry objects away from you at speeds that exceed the speed of light. It's not a violation of Einstein's theory of relativity, it's a consequence of it. This means that there are galaxies out there, real galaxies filled with stars and planets that are moving away from us faster than light can travel. Even if you could somehow hitch a ride on a photon and travel at the speed of light for eternity, you would never reach those galaxies. They're beyond what we call the cosmic horizon. The light they emit today will never reach Earth, not in a billion years, not in a trillion, never. And if this is blowing your mind right now, imagine what else is waiting for you on this channel. Science like this deserves to be shared. If you're enjoying this journey through the cosmos, please take a second to hit that subscribe button and give this video a thumbs up. It helps more people discover these incredible cosmic mysteries, and it keeps me motivated to bring you more content like this. Now let's keep going, because the story gets even stranger. The observable universe, the part of the universe we can actually see, has a boundary. That boundary is determined by the speed of light and the age of the universe. Since the universe is 13.8 billion years old, you might think we can see objects that are 13.8 billion light years away. But because the universe has been expanding this whole time, the actual radius of the observable universe is much larger, about 46.5 billion light years in every direction. That gives the observable universe a diameter of roughly 93 billion light years. But here's the thing, that's just what we can observe. The entire universe is almost certainly much, much bigger, maybe infinitely bigger. We simply have no way to see beyond that horizon. The light from anything farther away hasn't had enough time to reach us yet. And because the expansion of the universe is accelerating, driven by a mysterious force we call dark energy, some of that light never will. This acceleration was discovered in 1998 by two teams of astronomers studying distant supernovae. They expected to find that the universe's expansion was slowing down due to gravity. Instead, they found the opposite. The expansion is speeding up. It's as if someone is pressing the gas pedal on the universe, making it grow faster and faster with each passing moment. For this discovery, the scientists were awarded the Nobel Prize in Physics in 2011, and it fundamentally changed our understanding of the cosmos. Dark energy makes up about 68% of the total energy content of the universe. We don't know what it is. We don't know where it comes from. But we know what it does. It pushes space apart. And because of dark energy, the cosmic horizon is shrinking in a sense. Galaxies that we can see today will eventually disappear from view as they cross beyond the boundary where light can no longer reach us. So let's talk about what this actually means for you, for humanity, and for the future of exploration. Because this isn't just some abstract concept that only matters to physicists scribbling equations on chalkboards. This is about the ultimate limits of what we can know, where we can go, and what we can discover. Right now, astronomers are mapping the universe using the most powerful telescopes ever built. The James Webb Space Telescope, launched on December 25, 2021, orbits the Sun about 1 million miles from Earth. It's equipped with a mirror 21.3 feet across and instruments that can detect infrared light, the kind of light emitted by the most distant and ancient galaxies. Webb has already rewritten textbooks, It has discovered galaxies that formed earlier than we thought possible. It has analyzed the atmospheres of planets orbiting other stars, searching for signs of water vapor, methane, and carbon dioxide, molecules that could hint at life. And it has peered into stellar nurseries, watching new stars being born from clouds of gas and dust. But even the James Webb Space Telescope has limits. It can only see so far. It can only capture light that has actually reached us. And as we've just established, there are vast regions of space whose light will never arrive. Those regions are forever invisible, not because our technology isn't good enough, but because the laws of physics themselves prevent us from seeing them. Think about that for a moment. There are entire galaxies, maybe trillions of them, that we will never observe. There could be civilizations out there looking up at their own night sky, asking the same questions we are. They might have telescopes, they might have scientists, they might wonder if they're alone, and we will never know they exist. Not because we're not looking hard enough, but because the universe has drawn a line we cannot cross. This brings us to a concept called the particle horizon. The particle horizon is the boundary of the observable universe. It's the farthest distance from which light has had time to reach us since the Big Bang. Beyond that horizon, we simply cannot see. And because the universe is expanding, that horizon is constantly shifting. Every second, light from slightly more distant regions enters our observable universe. But at the same time, galaxies that are already near the edge are being pushed farther away by the expansion of space. Some of them are accelerating beyond the point of no return. Now you might be wondering, if light from distant galaxies is just now reaching us, does that mean we're seeing them as they were billions of years ago? Absolutely. In fact, when we observe the most distant galaxies, we're essentially looking at cosmic fossils. These galaxies might not even exist anymore in the form we see them. They've had billions of years to evolve, to merge with other galaxies, to form new stars, or perhaps to fade into darkness. We'll never know what they look like today because the light showing us their current state won't reach Earth for billions more years, if it ever does. Here's another mind-bending thought. Because the speed of light is finite, there's no such thing as now on a cosmic scale. When you look at the Moon, you see it as it was 1.3 seconds ago. When you look at the nearest star system, Alpha Centauri, you see it as it was 4.37 years ago. When you look at the center of our Milky Way galaxy, you see it as it was 26,000 years ago. There is no universal present moment. The universe is a patchwork of different times, all stitched together by the speed of light. And here's where it connects to something we've talked about before on this channel. If you're wondering why this matters for humanity's future among the stars, you should definitely check out my video called "This is Why We Are Stuck in the Solar System Forever." In that video, I dive deep into the practical challenges of interstellar travel, the vast distances, the energy requirements, and the brutal reality that even our closest neighboring star is so far away that reaching it would take tens of thousands of years with current technology. The link is in the description and on the card above. But let's get back to the expansion itself, because there's something truly strange happening, and scientists are still trying to figure it out. It's called the Hubble tension, and it's one of the biggest mysteries in cosmology today. Here's the problem. When astronomers measure the rate of the universe's expansion by observing distant supernovae and galaxies, they get one number for the Hubble constant, around 73 kilometers per second per megaparsec. But when they calculate the expansion rate using data from the cosmic microwave background, the afterglow of the Big Bang, they get a different number, closer to 67 kilometers per second per megaparsec. That might not sound like a huge difference, but in science, when two methods of measuring the same thing give you different answers, it means something is wrong. Either one of the measurements is off, or our understanding of the universe is incomplete. Researchers have checked and rechecked their work. They've used different telescopes, different methods, and different teams. and the tension remains. In late 2025, new measurements using gravitational lensing, where the gravity of a massive galaxy bends and magnifies the light from objects behind it, actually deepen the mystery. The numbers still don't match. Some scientists think this could be a sign of new physics, something we haven't discovered yet. Maybe dark energy isn't constant, maybe it's changing over time, maybe there's something else out there, some unknown force or particle influencing the expansion in ways we don't understand. And this is what I love about science. It's not about having all the answers. It's about asking better questions. It's about being humble enough to admit when we don't know something and curious enough to keep searching. So where does that leave us? We know the universe is expanding. We know that expansion is accelerating. We know that light, despite being the fastest thing in existence, can't keep up with the stretching of space itself. And we know that because of this, there are parts of the universe we will never see, never reach, and never fully understand. But instead of feeling defeated by that, I think we should feel inspired. Because even though there are limits to what we can see, there's still so much within our reach. The observable universe contains an estimated 2 trillion galaxies. Each of those galaxies has hundreds of billions of stars. Many of those stars have planets. And on some of those planets, conditions might be just right for life. We are living in a golden age of astronomy. For the first time in human history, we have the tools to study planets around other stars. We can analyze their atmospheres. We can detect water vapor, oxygen, and methane, gases that could indicate biological processes. Missions like the James Webb Space Telescope, the upcoming Nancy Grace Roman Space Telescope, and ground-based observatories like the Extremely Large Telescope in Chile are pushing the boundaries of what we can discover. And here's the beautiful irony. Even though the universe is expanding and parts of it are slipping beyond our reach, we're learning more about it now than ever before. Every year, new discoveries are made. Every year, our picture of the cosmos becomes a little clearer. We've mapped the cosmic microwave background with stunning precision. We've detected gravitational waves, ripples in space-time itself, caused by colliding black holes and neutron stars. We've photographed the event horizon of a black hole using a network of radio telescopes spanning the entire planet. We are part of the universe trying to understand itself. We are made of atoms that were forged in the cores of ancient stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stellar furnaces billions of years ago. When those stars died, they scattered their contents across space, and eventually that material came together to form our solar system, our planet. And you are not separate from the cosmos, you are a piece of it. And every question you ask, every moment of wonder you feel when you look up at the stars, that's the universe reflecting on its own existence. Now let's dive deeper into what happens when light travels through an expanding universe, because this is where things get truly bizarre. You see, light doesn't just travel through space like a car driving down a highway. Light is affected by the expansion of space itself, and that effect has profound consequences for what we observe. When a distant galaxy emits light, that light sets off on a journey toward us. But while the light is traveling, space is stretching. As space expands, the wavelength of the light stretches along with it. This is called cosmological redshift. The light gets shifted toward the red end of the spectrum. Longer wavelengths, lower energy. The farther away the galaxy is and the longer the light has been traveling, the more redshifted it becomes. Astronomers use redshift as a kind of cosmic ruler. By measuring how much the light from a galaxy has been redshifted, they can calculate how far away it is and how fast it's moving away from us. A redshift value of 0 means the object isn't moving away at all. A redshift of 1 means the universe has doubled in size since the light was emitted. The galaxy MOMZ14 I mentioned earlier, has a redshift of around 14, which means the universe has expanded 14 times over since that light began its journey. That's how we know we're seeing it, as it was only 280 million years after the Big Bang. But here's something that might surprise you. When we say a galaxy is 46 billion light-years away, that doesn't mean the light took 46 billion years to get here. Remember, the universe is only 13.8 billion years old. So how can something be farther away than the age of the universe multiplied by the speed of light? The answer is expansion. When the light left that distant galaxy, the galaxy was much closer to us. But during the billions of years the light was traveling, space itself stretched, carrying the galaxy farther and farther away. By the time the light reaches us, the galaxy is much more distant than it was when the light began its journey. This is why the observable universe has a radius of about 46.5 billion light-years, even though the universe is only 13.8 billion years old. The math works out because of the expansion. Space has been stretching the whole time, pushing the sources of the oldest light farther and farther away. Now let's talk about what this means for the future, because the expansion isn't just continuing, it's accelerating. And that acceleration has consequences that are both fascinating and a little bit haunting. Dark energy, the mysterious force driving the acceleration, was completely unknown until 1998. Before that, cosmologists assumed the universe's expansion would eventually slow down due to gravity. After all, every galaxy pulls on every other galaxy. That gravitational attraction should act like a brake, gradually slowing the expansion. Some scientists even thought the universe might one day stop expanding altogether and begin to contract, eventually collapsing back into a big crunch, a kind of reverse Big Bang. But when two independent teams of astronomers studied distant Type Ia supernovae, exploding stars that serve as cosmic distance markers, they found something shocking. The distant supernovae were dimmer than expected, which meant they were farther away than they should have been if the expansion was slowing down. The only explanation was that the expansion was actually speeding up. The universe wasn't just coasting, it was accelerating. This discovery was so unexpected that the scientists initially thought they'd made a mistake. They rechecked their data, they looked for errors, but the evidence was undeniable. The universe's expansion is accelerating, and it has been for the last several billion years. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the Nobel Prize in Physics in 2011 for this discovery. So what is dark energy? Honestly, we don't know. It's one of the biggest unsolved mysteries in all of physics. We know it exists because we can see its effects. It makes up about 68% of the total energy content of the universe. But we have no idea what it actually is. Some scientists think it might be a property of space itself, a kind of energy that's woven into the fabric of the vacuum. Others think it could be a new field, similar to the Higgs field, that permeates all of space. And some researchers have proposed that our understanding of gravity might be incomplete, and that what we call dark energy is actually a sign that Einstein's general relativity breaks down on cosmic scales. Whatever dark energy is, it's winning the cosmic tug-of-war against gravity. And because of that, galaxies are being pushed farther and farther apart. Right now, we can see about 2 trillion galaxies in the observable universe. But in the far future, trillions of years from now, most of those galaxies will have disappeared beyond the cosmic horizon. They'll be moving away from us faster than light, and their light will never reach us again. Imagine a civilization that arises in our galaxy 100 billion years from now. When they look up at the sky, they won't see the rich tapestry of galaxies that we see today. They'll see almost nothing. The sky will be dark except for the stars in their own galaxy. They won't be able to detect the cosmic microwave background because it will have been redshifted into oblivion They won't have any evidence of the Big Bang. They won't even know that the universe is expanding. As far as they can tell, their galaxy will be the entire universe, floating alone in an infinite void. We are incredibly fortunate to be living at a time when the universe is still young enough and close enough that we can study it. We can see the afterglow of the Big Bang. We can observe distant galaxies. We can measure the expansion. Future civilizations won't have that luxury. In a sense, we're living in the golden age of cosmology. But let's bring this back to the present because there's something even stranger happening right now. Not only is the universe expanding, but different parts of it are expanding at different rates. And this brings us back to the Hubble tension. When cosmologists measure the Hubble constant using observations of the early universe, specifically the cosmic microwave background, they get a value of about 67.4 kilometers per second per megaparsec. This measurement comes from the Planck satellite, which mapped the cosmic microwave background in exquisite detail between 2013 and 2018. The cosmic microwave background is the oldest light in the universe, emitted just 380,000 years after the Big Bang. By studying the tiny temperature fluctuations in this ancient light, scientists can infer the expansion rate of the universe. But when astronomers measure the Hubble constant using observations of the local universe, things like Cepheid variable stars, type Ia supernovae, and other distance indicators, they get a higher value, around 73.0 kilometers per second per megaparsec. This measurement comes from direct observations of objects relatively nearby, cosmically speaking. The difference between these two numbers might seem small, only about 8%. But in science, precision matters. And when two different methods of measuring the same fundamental constant give you different answers, it's a big deal. It suggests that either one of the methods is flawed, or there's something going on in the universe that we don't understand. Scientists have explored all kinds of possibilities. Maybe there's a systematic error in one of the measurements. Maybe the properties of type Ia supernovae aren't as consistent as we thought. Maybe the cosmic microwave background data has been misinterpreted, but after years of careful analysis, the tension remains. In fact, it's gotten worse. More precise measurements have only made the discrepancy more glaring. In December of 2025, astronomers using gravitational lensing, a technique where the gravity of a massive galaxy acts like a magnifying glass, bending and amplifying the light from more distant objects, published new measurements of the Hubble constant. They hoped this independent method would resolve the tension. Instead, it deepened the mystery. The new measurements fell somewhere between the two previous values, but they didn't match either one perfectly. The universe, it seems, is refusing to give us a simple answer. Some researchers now believe the Hubble tension could be pointing us toward new physics. Maybe dark energy isn't constant. Maybe it changes over time or varies from place to place. Maybe there's an unknown form of matter or energy affecting the expansion in unexpected ways. Or maybe, just maybe, our entire cosmological model, the lambda-cold dark matter model, which has been the foundation of cosmology for decades, needs to be revised. This is what makes science so exciting. We're not just filling in the details of a picture we already understand. We're discovering that the picture itself might be incomplete. And that means there are new discoveries waiting to be made, new mysteries waiting to be solved. So here we are. The fastest thing in the universe, light itself, is racing through space at a speed so great that it could circle the Earth 7.5 times in 1 second. And yet, it's not fast enough. It can't outrun the expansion of space. It can't reach every corner of the universe. There are galaxies it will never touch, stars it will never illuminate, and questions it will never answer. Let's take a step back and think about what all of this means on a human level, because when you really sit with these ideas, they can feel overwhelming. The universe is so vast, so old, and so fundamentally strange that it's easy to feel small and insignificant, but I want to offer you a different perspective. Yes, the universe is enormous. Yes, there are limits to what we can see and where we can go. But the very fact that we can understand these limits, that we can measure them and map them and grapple with their implications, that's nothing short of miraculous. Think about where we started. For most of human history, we didn't even know that other galaxies existed. In the early 1900s, astronomers thought the Milky Way was the entire universe. They saw fuzzy patches of light in the sky and assumed they were clouds of gas within our own galaxy. It wasn't until 1923 when Edwin Hubble, yes, the same Hubble the telescope is named after, measured the distance to the Andromeda galaxy that we realized the truth. Andromeda wasn't part of the Milky Way. It was a separate galaxy, an island universe, sitting 2.5 million light-years away. That discovery fundamentally changed our understanding of the cosmos. And Edwin Hubble didn't stop there. By 1929, he had made an even more profound discovery. He noticed that the farther away a galaxy was, the faster it appeared to be moving away from us. This wasn't because galaxies were fleeing from us specifically, it was because space itself was expanding. Every galaxy is moving away from every other galaxy. No matter where you are in the universe, it looks like everything is rushing away from you. This is what we now call Hubble's law, and it's one of the foundational pillars of modern cosmology. But here's what amazes me. Hubble made these discoveries using telescopes that, by today's standards, were tiny. The telescope at Mount Wilson Observatory, where he did much of his work, had a mirror just 100 inches across. Compare that to the James Webb Space Telescope, with its mirror over 21 feet wide, or the upcoming extremely large telescope in Chile, which will have a mirror over 128 feet across. We've come so far in just a century. And yet the questions Hubble was asking are the same questions we're still asking today. How big is the universe? How fast is it expanding? What is it made of? Where did it come from? And where is it going? Now let's talk about one of the most beautiful and poetic consequences of the finite speed of light. When you look up at the night sky, you're not just seeing distant objects, you're seeing the past. Every photon that enters your eye is a messenger from another time. The light from the sun is 8 minutes and 20 seconds old. The light from Proxima Centauri, the nearest star beyond our solar system, is 4.24 years old. The light from the Andromeda galaxy is 2.5 million years old, and the light from the most distant galaxies we can observe is over 13 billion years old. And this means that when you look at the universe, you're looking at a time machine. You're seeing layers of history, all stacked on top of each other. The sky is a living archive of cosmic evolution, and because different parts of the universe are at different distances, we can actually watch the story of the universe unfold. We can see galaxies in their infancy, just forming their first stars. We can see galaxies in their adolescence, actively building new stars and growing larger through mergers. And we can see galaxies in their old age, their star formation slowing down, their light growing dim. The James Webb Space Telescope was specifically designed to capture this story. By observing in infrared light, light with wavelengths longer than what our eyes can see, Webb can detect the heavily redshifted light from the most distant and ancient galaxies. And what it's found has been astonishing. Some of these early galaxies are far more massive and mature than we expected. They seem to have formed stars much faster than our models predicted. This has forced astronomers to rethink their theories about how galaxies grow and evolve. For example, in 2024 and 2025, Webb discovered several galaxies that appear to have formed within the first few 100 million years after the Big Bang. These galaxies are so bright and so massive that they challenge our understanding of how quickly matter could clump together under gravity. Some scientists have proposed that these early galaxies might have formed around primordial black holes that existed before the first stars. Others think that dark matter might have behaved differently in the early universe, allowing structures to form more rapidly. The truth is, we're still figuring it out. And that's okay. Science is a process, not a destination. But let's return to the central question: why isn't light fast enough? We've talked about the expansion of space, about dark energy, about the cosmic horizon. But there's another layer to this that's worth exploring. It's called the relativity of simultaneity, and it has to do with the very nature of time itself. According to Einstein's theory of special relativity, there is no universal now. Time is not absolute, depends on your frame of reference. If you're moving relative to me, we will disagree about whether two distant events happened at the same time. This isn't just a philosophical quirk, it's a real, measurable effect. Astronauts on the International Space Station age slightly slower than people on Earth because they're moving at high speed. GPS satellites have to account for relativistic effects, or they'd be off by miles within hours. Now, apply this to the universe. When we say a galaxy is 10 billion light-years away, we're talking about the distance light has traveled to reach us. But from the photon's perspective, if a photon could have a perspective, no time passes at all. Photons don't experience time. From the moment a photon is emitted to the moment it's absorbed, zero time elapses in its own frame of reference. To a photon, the entire journey is instantaneous. This is one of the strangest consequences of relativity. For us, light takes billions of years to cross the universe. For the light itself, the journey happens in an instant. There is no universal clock ticking away in the background. Time is woven into the fabric of space, and it bends and stretches along with it. So when we ask, why isn't light fast enough? We're really asking a deeper question about the nature of space, time, and causality. The speed of light isn't just a speed limit for objects moving through space. It's the speed at which cause and effect can propagate. It's the speed at which information can travel. And because the universe is expanding, there are regions of space that are so far away that no signal, no message, no information from us can ever reach them, and no signal from them can ever reach us. This creates what physicists call a causal horizon. Beyond this horizon, events are causally disconnected from us. They can't affect us, and we can't affect them. For all practical purposes, they might as well be in a separate universe, and as the expansion accelerates, that horizon is shrinking. More and more of the universe is slipping beyond our reach, becoming forever inaccessible. Now, I know this might sound depressing. It might feel like the universe is closing doors on us, locking away secrets we'll never be able to uncover. But I want you to consider another possibility. Maybe the fact that we can't see everything, that we can't know everything, is what makes the universe so compelling. Maybe the mystery is part of the beauty. Think about it. If the universe was small and simple, if we could see all of it and understand all of it with ease, would it still captivate us the way it does? Part of what makes science so thrilling is the chase. It's the process of pushing against the boundaries of knowledge, of finding new ways to ask old questions, of discovering that every answer leads to 10 more questions. And here's the thing, even though we can't see beyond the cosmic horizon, we can still learn an incredible amount from what's within our reach. The observable universe is enormous. It contains hundreds of billions of galaxies, each with hundreds of billions of stars. There are more stars in the observable universe than grains of sand on all the beaches on Earth. And we've only just begun to explore them. Every year, new telescopes come online. Every year, new techniques are developed. Gravitational wave astronomy, which detects ripples in space-time caused by colliding black holes and neutron stars, only became a reality in 2015. In less than a decade, it's already transformed our understanding of the universe. We've detected dozens of black hole mergers, observed neutron star collisions, and even started to map the population of black holes across cosmic time. Similarly, neutrino astronomy, using detectors buried deep underground or encased in ice at the South Pole, allows us to study the universe in a completely different way. Neutrinos are ghostly particles that barely interact with matter. Trillions of them pass through your body every second without you noticing. But by catching a few of them, scientists can study processes that are invisible to ordinary telescopes, like the nuclear reactions inside the Sun or the collapse of distant supernovae. And then there's the cosmic microwave background, that ancient light I mentioned earlier. It's been studied for decades, but every new measurement reveals something new. The Planck satellite gave us the most detailed map of the cosmic microwave background ever made, and it confirmed many predictions of the Big Bang theory, but it also raised new questions, like the Hubble tension we talked about. So let's dig into what happens at the very edge of what we can observe, because this is where the universe gets truly strange, where the rules we're familiar with start to break down in ways that challenge our intuition. We're going to explore the cosmic event horizon and what it means for the ultimate fate of everything. First, let's clarify something important. There are actually several different kinds of horizons in cosmology, and they mean different things. The particle horizon is the boundary of the observable universe, the farthest distance from which light has had time to reach us since the Big Bang. The event horizon is different. It's the boundary beyond which events happening now will never be observable to us in the future, no matter how long we wait. Because the expansion of the universe is accelerating, these two horizons don't coincide. The event horizon is actually closer than the particle horizon. Here's what that means in practice. There are galaxies we can see right now, galaxies whose light has reached us. But if those galaxies emit new light today, that light will never reach Earth. They've already crossed the event horizon. They're moving away from us so quickly that even light leaving them right now will be swept backward by the expansion of space. It's like trying to swim upstream in a river that's flowing faster than you can swim. You might make some progress at first, but eventually the current wins. This is profoundly strange when you really think about it. Right now, at this very moment, there are stars being born in distant galaxies. There are planets forming around those stars. Maybe there are even civilizations arising, building telescopes, asking the same questions we're asking, but we will never see any of it. The light from those events is already lost to us, swallowed by the accelerating expansion of space. And it gets stranger. Because the universe is accelerating, the event horizon is getting closer. Galaxies that are currently within our observable universe will eventually slip beyond the event horizon. Trillions of years from now, the night sky will be much emptier than it is today. Most of the galaxies we see now will have faded from view, their light redshifted into invisibility, their images frozen at the moment they crossed the horizon. But here's a fascinating detail. The light from those galaxies won't just disappear. It will become increasingly redshifted, stretched to longer and longer wavelengths, carrying less and less energy. Eventually, the light will be redshifted so much that it becomes undetectable. The galaxy will appear to freeze in time, growing dimmer and dimmer until it finally fades into darkness. From our perspective, it will look like the galaxy is moving in slow motion, its evolution grinding to a halt as it approaches the event horizon. This is actually similar to what happens near a black hole. If you watch someone fall into a black hole, you never actually see them cross the event horizon. From your perspective, they appear to slow down, their image growing dimmer and more red-shifted until they fade from view. Time dilation causes their clock to appear to run slower and slower relative to yours. The same thing happens with galaxies crossing the cosmic event horizon, except instead of gravity causing the effect, it's the expansion of space. Now let's think about what this means for the far future. Cosmologists have mapped out several possible scenarios for how the universe might end, and they all depend on the nature of dark energy. If dark energy remains constant, if it continues to push the universe apart at an accelerating rate, then we're headed for what's called the Big Freeze, or heat death. In this scenario, the universe will continue expanding forever. Stars will eventually run out of fuel and die. Galaxies will fade. Black holes will evaporate through a process called Hawking radiation, which takes an incomprehensibly long time, 10 to the 100th power years or more. Eventually, the universe will be cold, dark, and empty, with nothing but a thin soup of particles spread across an ever-expanding void. But there are other possibilities. If dark energy is not constant, if it's actually growing stronger over time, we could be headed for a big rip. In this scenario, the acceleration of the universe becomes so extreme that eventually even the forces holding atoms together can't withstand it. First, galaxy clusters are torn apart, then individual galaxies, then solar systems, then planets, then molecules, then atoms. Finally, even the nuclei of atoms are ripped to shreds. The universe doesn't just expand, it's torn apart at the seams. Fortunately, current observations suggest this scenario is unlikely, but we can't rule it out completely. There's also a scenario called the Big Crunch, which I mentioned earlier. In this case, the expansion of the universe eventually slows down, stops, and reverses. Gravity pulls everything back together, and the universe collapses into a singularity, a point of infinite density and temperature, essentially a reverse Big Bang. However, given that the universe's expansion is accelerating, not slowing down, this scenario seems very unlikely based on what we currently know. And then there's the possibility that we simply don't understand dark energy at all, and that the future of the universe is something we haven't even imagined yet. Maybe dark energy will decay over time, changing the expansion rate in unpredictable ways. Maybe it will trigger a phase transition like water freezing into ice, altering the fundamental properties of space itself. Maybe the universe will spawn new baby universes through a process called eternal inflation, creating an infinite multiverse where every possible outcome actually happens somewhere. The truth is, we don't know, and that's okay. Not knowing is the starting point for discovery. But let's bring this back to the here and now, because there's something important I want you to understand. Even though the universe is vast and ancient, even though there are limits to what we can see and where we can go, we are still connected to it in the most profound way possible. Every atom in your body was forged in the heart of a star. The hydrogen in your cells was created in the Big Bang itself within the first few minutes of the universe's existence. The heavier elements, carbon, nitrogen, oxygen, iron, were cooked up in the cores of stars over billions of years and then scattered into space when those stars exploded as supernovae. You are not made of Earth. You are made of stars. You are stardust, shaped by billions of years of cosmic evolution into a form capable of looking back at the universe and asking, where did I come from? That's not just poetic, it's literally true. The universe has arranged itself in such a way that a small part of it, you, can contemplate the whole. You are the universe observing itself. And here's the beautiful part. You're not alone in this. Every person you've ever met, every animal, every plant, every living thing on this planet is made of the same stardust. We are all cousins, all connected through deep time to the very first stars that lit up the cosmos. And beyond Earth, there are likely countless other worlds where the universe has become aware of itself in different forms, asking the same questions under different skies. This is why I find cosmology so deeply moving. It's not just about abstract equations and distant galaxies. It's about understanding our place in the grand story of existence. It's about recognizing that we are part of something much larger than ourselves, something that stretches back 13.8 billion years and will continue for trillions of years into the future. And even though light isn't fast enough to reach every corner of the universe, even though there are limits to what we can know, we can still do something remarkable. We can look up at the night sky and see photons that have been traveling for billions of years just to end their journey in our eyes. We can build telescopes and detectors that allow us to witness the birth of galaxies, the death of stars, and the collision of black holes. We can use mathematics and physics to peer beyond the observable universe and make predictions about what lies beyond. We can imagine, we can wonder, we can ask questions that no one has ever asked before. And sometimes, if we're clever and persistent, we can find answers. This is the human adventure. This is what separates us from rocks and trees and rivers. We have the capacity to understand the universe, to marvel at it, to feel connected to it. And that capacity is, in my opinion, one of the most precious things in all of existence. So yes, the fastest thing in the universe isn't fast enough. Light is bound by the expansion of space, trapped by the acceleration, driven by dark energy. There are galaxies it will never reach, secrets it will never reveal, but that doesn't diminish the wonder of what we can see. It doesn't make the universe any less magnificent. If anything, it makes it more so because it reminds us that the cosmos is not a simple, static thing. It's dynamic, it's evolving, it's full of surprises, and we get to be here, right now, at this moment in cosmic history, watching it all unfold. We get to ask the biggest questions imaginable. We get to push against the boundaries of knowledge and see what we find. We get to be explorers, not of distant lands, but of space and time itself. That's something worth celebrating. Now, I want to take you on a journey through some of the most mind-bending observations we've made about the universe, observations that highlight just how strange and wonderful the cosmos really is. Because when you understand what scientists have actually seen and measured, the reality becomes even more extraordinary than fiction. Let's start with something that changed astronomy forever: the cosmic microwave background. This is the oldest light in the universe, and it's everywhere. Right now, as you're listening to this, you're bathed in this ancient radiation. It fills every cubic centimeter of space. If you could see in microwave wavelengths, the entire sky would glow with a faint, almost uniform light. This is the afterglow of the Big Bang itself, the remnant heat from when the universe was so hot and dense that atoms couldn't even form. Here's what happened. In the early universe, about 380,000 years after the Big Bang, the temperature finally dropped low enough for electrons and protons to combine and form neutral hydrogen atoms. Before this moment, the universe was opaque. Photons couldn't travel very far before bumping into free electrons. But once atoms formed, the universe became transparent. Light could suddenly travel freely through space. The photons that were released at that moment have been traveling ever since, and we can still detect them today. But here's the incredible part. Because the universe has expanded so much since then, those photons have been stretched. They started out as visible and ultraviolet light, but now they're microwaves with wavelengths measured in millimeters. The temperature of this radiation is about 2.7 degrees above absolute zero, incredibly cold, but still measurable. And by studying the tiny temperature fluctuations in this radiation, fluctuations of just a few millionths of a degree, scientists can learn about the structure and composition of the early universe. The cosmic microwave background is like a baby picture of the universe. It shows us what the cosmos looked like when it was just an infant. And the details are astonishing. The fluctuations in temperature correspond to regions of slightly higher and lower density. The denser regions eventually collapsed under gravity to form the first galaxies and galaxy clusters. The pattern of these fluctuations tells us about the geometry of space, the amount of dark matter and dark energy, and the rate of expansion. It's one of the most important pieces of evidence supporting the Big Bang theory. But the cosmic microwave background also raises profound questions. For example, the temperature is remarkably uniform across the entire sky. Regions that are on opposite sides of the sky, separated by billions of light years, have almost exactly the same temperature. How is that possible? Those regions were never in contact with each other. Light from one side couldn't have reached the other side in the time since the Big Bang, so how did they end up at the same temperature? This is called the horizon problem, and the leading explanation is something called cosmic inflation. In the first tiny fraction of a second after the Big Bang, we're talking about 10 to the negative 36 seconds, the universe underwent a period of exponential expansion. Space expanded faster than the speed of light, growing by a factor of at least 10 to the 26th in an unimaginably short time. This rapid expansion stretched a tiny, uniform region into something much larger, which is why the cosmic microwave background looks so uniform today. Inflation is one of the most successful ideas in cosmology, but it's also one of the strangest. It suggests that for a brief moment, the universe expanded faster than light could travel through it. And remember, nothing can move through space faster than light, but space itself has no such speed limit. During inflation, space was expanding so rapidly that particles on opposite sides of the universe were moving away from each other faster than light could travel between them. This is the same phenomenon we see today with distant galaxies, just happening much, much faster. Now let's talk about another astonishing discovery: gravitational waves. For over a century, Einstein's theory of general relativity predicted that massive objects accelerating through space should create ripples in space-time itself, waves of gravity that propagate outward at the speed of light. But these waves are incredibly weak. Even the most violent cosmic events produce gravitational waves that are barely detectable. For decades, scientists tried and failed to detect them directly. Then, on September 14, 2015, something extraordinary happened. Two detectors, part of the Laser Interferometer Gravitational Wave Observatory, or LIGO, located in Louisiana and Washington State, simultaneously detected a signal. It was faint, lasting only a fraction of a second, but it was unmistakable. Two black holes, each about 30 times the mass of the Sun, had spiraled into each other and merged, releasing an enormous burst of energy in the form of gravitational waves. The collision happened 1.3 billion light-years away, and the waves had been traveling through space ever since, until they finally reached Earth. This was a monumental achievement. It confirmed one of the last major predictions of general relativity, and it opened an entirely new way of observing the universe. Since that first detection, dozens more gravitational wave events have been observed. We've seen black holes colliding, neutron stars merging, and even hints of more exotic objects. Gravitational wave astronomy allows us to study phenomena that are invisible to traditional telescopes. Black holes don't emit light, but when they collide, they shake the fabric of space-time itself, and we can detect those shakes. And here's the beautiful thing: gravitational waves travel at the speed of light, but they're not affected by anything along the way. Light can be absorbed or scattered by dust and gas. Gravitational waves just pass right through. They carry information about events that would be completely hidden from ordinary telescopes. This opens up the possibility of studying the universe in ways we never could before. In fact, scientists are now planning even more sensitive gravitational wave detectors. The Laser Interferometer, Space Antenna, or LISA, will be a space-based detector capable of observing gravitational waves from supermassive black hole mergers, events so powerful they can be detected across the entire universe. LISA is scheduled to launch in the 2030s, and it promises to revolutionize our understanding of how galaxies and black holes evolve over cosmic time. But let's get back to the speed of light, because there's another aspect of this that I think you'll find fascinating. Light doesn't always travel at the same Speed? Wait, didn't I just spend this entire video telling you that the speed of light is constant? Well, yes and no. The speed of light in a vacuum, empty space, is always the same. 299,792,458 meters per second. That number never changes. But when light travels through a material like water, glass, or air, it slows down. This happens because light interacts with the atoms in the material. Photons are absorbed and re-emitted by electrons, and this process takes time. The more dense the material, the slower light travels through it. In water, light moves at about 75% the speed it travels in a vacuum. In glass, it's even slower. And in some specially prepared materials, scientists have slowed light down to just a few meters per second, slower than a person walking. In fact, in 1999, a team of physicists led by Lena Howe managed to slow light down to just 17 meters per second using a cloud of ultra-cold atoms called a Bose-Einstein condensate. And in 2013, researchers actually brought light to a complete stop, storing the information carried by photons in the quantum states of atoms, then releasing it later. This kind of research has implications for quantum computing and communication, where controlling the speed and behavior of light could be incredibly useful. But here's the key point. Even though light can be slowed down in materials, the fundamental speed limit of the universe, the speed of light in a vacuum, remains unchanged. And that speed limit is woven into the very fabric of space-time. It's not just about light, it's about causality, about the maximum speed at which information can travel, about the structure of reality itself. Einstein's theory of special relativity tells us that as you approach the speed of light, strange things happen. Time slows down, lengths contract, mass increases. If you were on a spaceship traveling at 99% the speed of light, time would pass much more slowly for you than for people back on Earth. You could travel to a distant star and back, and while only a few years might pass for you, decades or even centuries might pass on Earth. This is called time dilation, and it's not science fiction, it's real physics, confirmed by countless experiments. In fact, we see time dilation in action all the time. Muons are subatomic particles created when cosmic rays hit the upper atmosphere. They're unstable and decay in about 2 microseconds. At the speeds they're traveling, they shouldn't be able to reach the ground before decaying. But because they're moving so fast, time passes more slowly for them from our perspective. They live longer, and many of them make it to the surface. We can detect them. Without time dilation, we wouldn't see them at all. This connection between space and time is what makes the speed of light so fundamental. It's not just a speed, it's the conversion factor between space and time. It's the exchange rate between distance and duration. And it's the same everywhere in the universe for everyone, no matter how fast they're moving. Or this is what Einstein meant when he said, the laws of physics are the same in all inertial reference frames. But here's the mind-bending part. Even though the speed of light is constant, the universe can still expand faster than light. Space itself isn't bound by the speed limit. And this brings us back to where we started. The fastest thing in the universe still isn't fast enough. Let's explore what this cosmic speed limit means for the future of humanity, because when we talk about the expansion of the universe and the limits of light, we're not just talking about abstract physics. We're talking about the ultimate boundaries of what we can explore, what we can discover, and what we can become as a species. Right now, humanity is confined to one small planet orbiting an average star in the outer suburbs of the Milky Way galaxy. We've sent robotic probes to every planet in our solar system. We've landed rovers on Mars. We've flown past Pluto and ventured into interstellar space with the Voyager probes. but in cosmic terms, we've barely left home. The farthest human-made object, Voyager 1, is currently about 15 billion miles from Earth. That sounds impressive until you realize that the nearest star system, Alpha Centauri, is about 25 trillion miles away. Voyager 1 is moving at about 38,000 miles per hour, and at that speed, it would take over 70,000 years to reach Alpha Centauri. And that's just our nearest neighbor. The Milky Way galaxy is about 100,000 light-years across. That means light takes 100,000 years to travel from one side to the other. If we wanted to explore even a tiny fraction of our own galaxy using conventional rockets, it would take millions or billions of years. And beyond our galaxy, the distances become almost incomprehensible. Andromeda, our nearest major galactic neighbor, is 2.5 million light-years away. The Virgo cluster, a large collection of galaxies, is about 54 million light-years away. And the most distant galaxies we can observe are over 13 billion light-years away. Given these distances, how could we ever hope to explore the universe? Even if we could build a spaceship that travels at a significant fraction of the speed of light, say 10%, it would still take 43 years to reach Alpha Centauri, and accelerating a spacecraft to that speed would require an enormous amount of energy. To accelerate just 1 kilogram of mass to 10%, the speed of light requires about 450 trillion joules of energy. That's roughly the total energy output of a large power plant running for several days, just to move 1 kilogram. A spacecraft capable of carrying humans and supplies would weigh thousands of kilograms. The energy requirements are staggering. Some scientists have proposed theoretical solutions. One idea is the Generation Ship, a massive spacecraft designed to support a crew for multiple generations. The original crew would never reach the destination. Their children, grandchildren, and perhaps great-great-great-grandchildren would be the ones to arrive. This raises profound ethical and psychological questions. What kind of society would develop on such a ship? Would the descendants even want to continue the mission? Would they remember why they're traveling? Another idea is suspended animation or cryogenic freezing, where the crew is placed in a state of hibernation for the duration of the journey. This remains purely theoretical for humans, although some animals can naturally enter states of suspended animation. If we could perfect this technology, interstellar travel might become more feasible. But there are still enormous technical challenges, and we're nowhere close to making it work for humans. Then there's the concept of the light sail, a spacecraft propelled by powerful lasers or the pressure of sunlight against a large, reflective sail. In 2016, physicist Stephen Hawking and entrepreneur Yuri Milner announced the Breakthrough Starshot project, which aims to send tiny, lightweight probes to Alpha Centauri using this method. The idea is to build thousands of small spacecraft, each weighing just a few grams, and accelerate them to 20% the speed of light using ground-based lasers. At that speed, they could reach Alpha Centauri in about 20 years. The probes would be too small to carry humans, but they could carry cameras and instruments to send back data. It's an ambitious project, and there are many technical hurdles to overcome, but it represents one of the most serious attempts to achieve interstellar travel in the near future. But even if we solve the engineering challenges, even if we find a way to travel at a significant fraction of the speed of light, the expansion of the universe still limits how far we can go. Remember, galaxies beyond a certain distance are receding from us faster than light. No matter how fast we travel, we can never reach them. They are fundamentally inaccessible, and because the expansion is accelerating, more and more galaxies are crossing beyond that boundary every moment. This means that the reachable universe, the part we could theoretically visit if we had unlimited time and technology, is actually quite small compared to the observable universe. Right now, we could, in principle, reach any galaxy within about 18 billion light-years, assuming we could travel at close to the speed of light and had enough time. But galaxies farther than that are already moving away too fast. Even if we left today at the speed of light, we would never catch up. And it gets worse. Because the expansion is accelerating, the reachable universe is shrinking. Every second that passes, galaxies that were within reach slip beyond the cosmic event horizon. In a sense, the universe is closing doors on us. The longer we wait, the fewer galaxies we'll be able to explore. This has led some scientists to propose something called the cosmic imperative, the idea that if humanity wants to become a truly spacefaring civilization, we need to act sooner rather than later. Every year we delay is a year that the reachable universe shrinks. Of course, this is still wildly theoretical. We're nowhere near the level of technology required for intergalactic travel. But it's an interesting thought experiment, and it highlights just how significant the expansion of the universe really is. Now let's think about communication. Even if we can't physically travel to distant galaxies, could we at least communicate with them? Could we send signals, share information, make contact with other civilizations? Again, the speed of light is the limiting factor. Radio waves, which we use for most long-distance communication, travel at the speed of light. If we sent a message to a galaxy 1 billion light-years away, it would take 1 billion years to get there. And if they sent a reply, it would take another billion years to reach us. That's a 2 billion-year round trip. Civilizations rise and fall in less time than that. By the time we received a response, humanity might not even exist anymore. Even within our own galaxy, communication is challenging. If we detected a signal from a civilization on the other side of the Milky Way, say 80,000 light-years away, it would take 80,000 years for our reply to reach them. That's not a conversation. That's a message in a bottle sent into the cosmic ocean with no guarantee anyone will ever read it. And yet we keep trying. Since 1974, we've sent deliberate messages into space, hoping that someone might be listening. The Arecibo message, transmitted from the Arecibo Observatory in Puerto Rico, was a 3-minute radio signal sent toward a globular star cluster about 25,000 light-years away. It contained basic information about humanity, our biology, our solar system, and our location. If anyone receives it and responds immediately, we'll get an answer in about 50,000 years. We've also sent physical messages. The Voyager spacecraft carry golden records, phonograph records containing sounds and images from Earth, along with instructions on how to play them. These records are intended for any intelligent beings who might encounter the spacecraft in the distant future. Voyager 1 is currently the farthest human-made object from Earth, but it's moving slowly in cosmic terms. It will take about 40,000 years to pass within a few light-years of another star. The chances of it being found are astronomically small, but it's a poetic gesture, a message from humanity to the universe saying, "We were here, we wondered, we hoped." But here's the thing. Despite the vast distances, despite the speed limit of light, despite the expansion of the universe, we keep searching. We keep building bigger telescopes, we keep sending out signals, we keep looking for signs of life. Because even though the universe is enormous and mostly empty, even though the odds of finding another civilization are incredibly small, the possibility alone is enough to drive us forward. The search for extraterrestrial intelligence, or SETI, has been scanning the skies for radio signals from alien civilizations for over 60 years. So far, we've found nothing conclusive, but the search continues using ever more sophisticated equipment and techniques. The Allen Telescope Array in California, the Green Bank Telescope in West Virginia, and the Meerkat Telescope in South Africa are all involved in SETI research. And with the advent of new technologies like machine learning, we're able to process and analyze data faster than ever before. In 2020, researchers launched a project called Breakthrough Listen, funded by Yuri Milner, the same entrepreneur behind Breakthrough Starshot. This project is surveying 1 million nearby stars, the 100 nearest galaxies, and the plane of the Milky Way for signs of intelligent life. It's the most comprehensive search ever undertaken, and it's still ongoing. So far, no confirmed detections, but every negative result teaches us something. It narrows down the possibilities. It helps us refine our search strategies. And there's another approach, looking for techno-signatures, evidence of advanced technology. Instead of listening for radio signals, we could look for signs of megastructures like Dyson spheres. Hypothetical constructs that a very advanced civilization might build around a star to capture all its energy. We could look for atmospheric pollution on distant planets, signs of industrial activity. We could search for laser pulses, waste heat, or other anomalies that don't occur naturally. The point is, we're not giving up. Even though the universe is vast and the speed of light is finite, even though there are fundamental limits to what we can reach and what we can know, we keep pushing forward because that's what humans do. We explore, we question, we dream. Now let's talk about something that might surprise you. The universe isn't just expanding, it's expanding in a way that's deeply connected to its beginning. And understanding this connection helps us grasp why light, despite being the fastest thing in existence, is still racing against an opponent it can never beat. Think about the Big Bang for a moment. It wasn't an explosion in space, it was an explosion of space itself. Every point in the universe was once compressed into an infinitesimally small region, and then suddenly space began to stretch. But here's the crucial detail, that stretching didn't happen from a center. There was no central point where the Big Bang occurred. It happened everywhere, all at once. Every location in the universe today was once part of that original singularity. This is one of the hardest concepts in cosmology to wrap your head around. When you picture an explosion, you naturally imagine it expanding outward from some central point into empty space. But the Big Bang wasn't like that. Space itself came into existence with the Big Bang. There was no outside for it to expand into. The universe didn't expand into anything, it just expanded. And it's still expanding now, carrying galaxies along with it like raisins in rising bread dough. This means that when we ask, what's beyond the edge of the universe? The question doesn't really make sense. There is no edge, or rather, if there is an edge, it's beyond the observable universe, beyond the cosmic horizon, beyond anything we can ever see or measure. The universe might be infinite. It might curve back on itself like the surface of a sphere. We don't know. And because of the limits imposed by the speed of light and the expansion of space, we may never know. But let's dig deeper into the early moments of the universe, because that's where some of the most fascinating physics happens. In the first fraction of a second after the Big Bang, the universe was unimaginably hot and dense. Temperatures were trillions of degrees. Matter, as we know it, couldn't exist. Instead, the universe was filled with a seething soup of fundamental particles, quarks, gluons, electrons, photons, all colliding and interacting at incredible energies. As the universe expanded, it cooled. Within the first microsecond, quarks combined to form protons and neutrons. Within the first 3 minutes, protons and neutrons fused to create the first atomic nuclei, mostly hydrogen and helium, with trace amounts of lithium. This process is called Big Bang nucleosynthesis, and it's one of the key pieces of evidence supporting the Big Bang theory. The ratios of hydrogen to helium to lithium that we observe in the universe today match the predictions of Big Bang nucleosynthesis almost perfectly. But atoms didn't form immediately. For the next 380,000 years, the universe was still too hot. Electrons couldn't bind to nuclei because they were constantly being knocked loose by high-energy photons. The universe was opaque, a glowing fog of ionized plasma. Then, as the temperature dropped below about 3,000 degrees Kelvin, electrons and nuclei combined to form neutral atoms. This moment is called recombination, and it's when the cosmic microwave background was released. Now here's where it gets really interesting. During the period of cosmic inflation, that exponential expansion in the first fraction of a second, tiny quantum fluctuations were stretched to cosmic scales. These fluctuations became the seeds for all the structure we see in the universe today. Regions that were slightly denser than average attracted more matter through gravity. Over time, these regions grew into stars, galaxies, and galaxy clusters. The pattern of these fluctuations is imprinted in the cosmic microwave background, and we can see it today with incredible precision. The Planck satellite, which observed the cosmic microwave background from 2013 to 2018, produced the most detailed map of these fluctuations ever made. The data from Planck has allowed cosmologists to measure the age of the universe, the density of matter and energy, the geometry of space, and the rate of expansion with unprecedented accuracy. And yet, despite all this precision, mysteries remain, like the Hubble tension we discussed earlier. But there's another profound mystery lurking in the early universe, the matter-antimatter asymmetry. According to our current understanding of particle physics, the Big Bang should have produced equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other, producing pure energy. If the universe started with equal amounts of both, they should have annihilated completely, leaving nothing but radiation. And yet here we are. The universe is made almost entirely of matter, with very little antimatter. Somehow there was a slight imbalance, about one extra matter particle for every billion matter-antimatter pairs. That tiny excess is what survived the annihilation and went on to form everything we see today. Why was there this imbalance? We don't know. It's one of the biggest unsolved problems in physics. Scientists are studying the properties of particles and antiparticles in particle accelerators like the Large Hadron Collider, looking for subtle differences that might explain the asymmetry. So far, we've found small differences in the behavior of certain particles and their antiparticles, but not enough to fully explain why matter won out over antimatter. This is an active area of research, and the answer could fundamentally change our understanding of physics. Let's shift gears now and talk about dark matter, because it's intimately connected to the expansion of the universe and the formation of structure. Dark matter makes up about 27% of the universe's total energy content. We can't see it directly. It doesn't emit, absorb, or reflect light, but we know it's there because of its gravitational effects. Galaxies rotate faster than they should based on the visible matter alone. Galaxy clusters hold together more strongly than the gravity from their visible matter can account for. And the distribution of galaxies across the universe follows patterns that only make sense if there's a lot more matter than we can see. The leading theory is that dark matter is made of particles that interact very weakly with ordinary matter. These particles, often called WIMPs, weakly interacting massive particles, would pass through normal matter almost as if it weren't there. Scientists have built detectors deep underground, shielded from cosmic rays and other background radiation, trying to catch the rare interaction of a dark matter particle with ordinary atoms. So far, these experiments haven't produced a definitive detection, but the search continues. There are also other candidates for dark matter. Axions are hypothetical particles that would be much lighter than WIMPs. Primordial black holes that formed in the early universe before the first stars, are another possibility. And some scientists think dark matter might be something even more exotic, like a manifestation of extra dimensions or a modification of gravity itself. Whatever dark matter is, it played a crucial role in the formation of galaxies. In the early universe, dark matter clumped together under gravity, creating dense regions that attracted ordinary matter. Gas fell into these dark matter halos and eventually formed stars and galaxies. Without dark matter, the universe would look completely different. Galaxies might not have formed at all, or they would have formed much later. The cosmic web, the large-scale structure of the universe with its filaments, walls, and voids, is shaped by dark matter. And here's the connection to the expansion of the universe. Dark matter acts as a brake on the expansion, pulling things together through gravity. Dark energy, on the other hand, acts as an accelerator, pushing things apart. The balance between these two forces determines the fate of the universe. For the first several billion years, dark matter dominated and the expansion was slowing down. But about 5 to 6 billion years ago, dark energy took over and the expansion started to accelerate. We're now living in an era where dark energy is winning and the universe is expanding faster and faster. This has profound implications. If dark energy remains constant, the universe will continue expanding forever, becoming colder, darker, and more empty with each passing eon. But if dark energy changes over time, if it gets stronger, weaker, or even changes sign, then the future could be very different. This is why measuring the expansion rate with precision is so important. It tells us not just where the universe has been, but where it's going. Now let's come back to the speed of light one more time, because there's a philosophical dimension to all of this that I think is worth exploring. The fact that light has a finite speed means that we are fundamentally isolated from much of the universe. There are events happening right now, stars exploding, planets forming, maybe even civilizations thriving, that we will never witness. The information about those events is traveling toward us at the speed of light, but if they're far enough away, that information will never arrive. This creates a kind of cosmic loneliness. We are surrounded by a vast universe, but we can only see and interact with a small fraction of it. The rest is beyond our reach, hidden behind horizons we cannot cross. And as the universe continues to expand and accelerate, those horizons are moving closer. The observable universe is, in a sense, shrinking. Not in physical size, it's still growing, but in terms of what we can potentially reach or communicate with. But here's another way to look at it. The very fact that we understand these limits is remarkable. 100 years ago, we didn't even know other galaxies existed. 50 years ago, we didn't know the universe's expansion was accelerating. 20 years ago, we hadn't detected gravitational waves or imaged a black hole. Every generation pushes the boundaries a little further, discovers a little more, understands a little better. And we do this with tools that are fundamentally limited by the speed of light. Our telescopes can only collect photons. Our gravitational wave detectors can only sense ripples traveling at the speed of light. Our neutrino observatories can only catch particles moving at nearly the speed of light. Everything we know about the universe comes to us through signals that respect this cosmic speed limit. Let's explore one of the most profound implications of everything we've discussed: the nature of observation itself and how the speed of light shapes not just what we can see, but what we can know about reality. When you look at anything, a tree, a person, a star, you're not seeing it as it is right now. You're seeing it as it was when the light left it. For objects on Earth, this delay is so small it's imperceptible. Light travels about 1 foot in a nanosecond, so when you look at someone standing across the room, you're seeing them as they were maybe 10 nanoseconds ago. Your brain can't process information that quickly anyway, so this delay is completely irrelevant to everyday life. But when we look at the cosmos, this delay becomes the dominant feature of observation. The sun is 8 light minutes away. If it suddenly vanished, we wouldn't know for 8 minutes. We'd continue to see it shining in the sky, receiving its light and warmth, completely unaware that it was already gone. When those 8 minutes passed, the sun would blink out of existence from our perspective, and simultaneously, we'd lose its gravitational pull. Earth would stop orbiting and fly off in a straight line into space. This thought experiment reveals something fundamental. Information, cannot travel faster than light. Not visual information, not gravitational information, not any kind of information. The speed of light isn't just about photons, it's about causality itself. It's the maximum speed at which cause and effect can propagate through the universe. Now extend this to the entire cosmos. Every photon that enters your eye, every particle that hits a detector, every wave that ripples through space-time, all of these are messages from the past. The universe we observe is a patchwork of different times, all layered on top of each other. The Moon is 1.3 seconds in the past. Alpha Centauri is 4.37 years in the past. The Andromeda Galaxy is 2.5 million years in the past. The cosmic microwave background is 13.8 billion years in the past. There is no way to see the universe as it is right now across all of space. The concept of now only makes sense locally. Einstein's relativity tells us that simultaneity, the idea that two events happen at the same time, depends on your frame of reference. Two observers moving relative to each other will disagree about whether distant events are simultaneous. Time is not absolute, it's relative, woven together with space into a four-dimensional fabric called space-time. This has strange consequences. Imagine two civilizations, one on Earth and one in a galaxy a billion light-years away. If they could somehow see each other, if the light could reach them, they would each see the other as it was a billion years ago. From Earth's perspective, that distant civilization is in our past. From their perspective, Earth is in their past. But from each civilization's own perspective, they exist in the present. Who's right? They both are. There is no universal now. The present moment is local, personal, relative. This is why, when people ask whether there's life elsewhere in the universe right now, the question is more complicated than it seems. What do we mean by right now? In our frame of reference? In their frame of reference? If a civilization exists in a galaxy 10 billion light-years away, and we could somehow see them, we'd be seeing them as they were 10 billion years ago. They might not even exist anymore. Or they might have evolved into something completely unrecognizable. We'll never know their now, because the information about their current state is 10 billion years away from reaching us. And here's the truly mind-bending part. If the universe is infinite, then somewhere out there, unimaginably far away, beyond countless cosmic horizons, there might be another region of space that looks exactly like ours. The laws of probability suggest that if you have infinite space and finite arrangements of matter, every possible configuration must eventually repeat. There could be another Earth, another version of you living a life identical to yours, or slightly different, or wildly different. An infinite universe would contain infinite versions of everything, but we can never reach those regions. We can never see them. They are beyond the cosmic event horizon, separated from us by the expansion of space. For all practical purposes, they might as well not exist. They are causally disconnected from us, unable to affect us, unable to be affected by us. In a very real sense, they are in a separate universe. This brings us to an idea that's been gaining traction in recent years, the multiverse. Not in the science fiction sense of parallel dimensions, but in the cosmological sense of separate regions of space that can never interact with each other. If cosmic inflation happened the way many scientists think it did, then our observable universe might just be one bubble in an eternally inflating space. Other bubbles, other universes would exist, each with its own laws of physics, its own constants of nature, its own history. These other universes would be forever beyond our reach, separated not by distance, but by the very structure of space-time. We could never travel to them, never see them, never confirm their existence, and yet the mathematics of inflation seems to suggest they exist. This is controversial, of course. Some scientists argue that if something can never be observed or tested, it's not science, it's philosophy or metaphysics. Others counter that the multiverse is a natural prediction of our best theories, and we shouldn't ignore it just because it's unobservable. But let's bring this back down to Earth, literally. Because while we're thinking about cosmic horizons and unreachable universes, there's a horizon much closer to home that affects us directly. The horizon of our own galaxy. The Milky Way is our cosmic home, a barred spiral galaxy containing somewhere between 100 billion and 400 billion stars. It's about 100,000 light-years across, and our Sun sits about 26,000 light-years from the galactic center, out in one of the spiral arms. We're orbiting the center of the galaxy at about 500,000 miles per hour, completing one full orbit every 225 to 250 million years. The last time we were in this position in our orbit, dinosaurs were just beginning to dominate the Earth. The Milky Way is part of a larger structure called the Local Group, which contains about 80 galaxies. The two largest are the Milky Way and Andromeda, and they're actually on a collision course. In about 4 to 5 billion years, they'll merge into a single, larger galaxy that astronomers have already nicknamed Milkomeda. Don't worry though, the distances between stars are so vast that actual collisions between stars will be incredibly rare. The night sky will look spectacular though, as the two galaxies interpenetrate and gravitational forces fling stars into new orbits. The Local Group is part of an even larger structure called the Laniakea supercluster, which contains about 100,000 galaxies spanning 520 million light-years. And Laniakea is just one of millions of superclusters in the observable universe. The universe is organized into a cosmic web of filaments and walls, with vast empty voids between them. This structure formed from those tiny quantum fluctuations in the early universe, amplified by billions of years of gravitational evolution. Now here's the key point. Everything in the Local Group is gravitationally bound together. That means the expansion of the universe isn't pulling these galaxies apart. Gravity is strong enough to hold them together. But beyond the Local Group, most galaxies are receding from us due to the expansion of space. And the farther away they are, the faster they're receding. This means that in the far future, long after the Milky Way and Andromeda have merged, long after the smaller galaxies in the Local Group have been absorbed, the descendants of humanity, if we're still around, will live in a galaxy that's increasingly isolated. The other galaxies will have receded beyond the cosmic horizon. The sky will be dark except for the stars in our own galaxy. Future astronomers will have no evidence of the Big Bang, no way to measure the expansion of the universe, no way to know that there are other galaxies at all. In a sense, we're living in a privileged time. We can see the universe in its youth, we can observe its expansion, we can study its history. Future civilizations will have a much more limited view. They'll be locked inside their own galaxy, unaware of the vast cosmos beyond, unless they have records, unless they preserve the knowledge we're gathering now. This is one reason why some scientists argue that documenting our observations is so important. We're not just learning for ourselves, we're potentially creating a record for future generations who won't be able to make these observations themselves. There's something poetic about that. The universe is giving us a window of time, a few billion years, maybe 10 or 20 billion at most, during which we can observe its true nature. Before us, no intelligent observers existed. After us, the view will be obscured. We happen to exist at just the right time, in just the right place, to see the universe for what it really is. Is that coincidence, or is there something deeper going on? This is where science meets philosophy. Some researchers invoke the anthropic principle, the idea that we observe the universe to be the way it is because if it were different, we wouldn't be here to observe it. The universe has to be old enough for stars to form and create heavy elements, for planets to form, for life to evolve, and for intelligence to emerge. We exist about 14 billion years into the universe's history because that's roughly how long it takes for observers like us to appear. But the anthropic principle doesn't explain everything. It doesn't tell us why the universe has the specific properties it does, or why the laws of physics take the form they take. These are deep questions and we don't have complete answers. But that's okay. The search for answers is what drives science forward. So here we are, at the end of our journey through space, time, and the limits of light. Let's bring it all together and think about what this means, not just for science, but for us, for humanity, for the future. The fastest thing in the universe travels at 299,792,458 meters per second. Nothing can go faster, not particles, not information, not cause and effect. This speed is woven into the very fabric of reality, into the equations that govern how space and time interact, into the fundamental structure of the cosmos. And yet, despite being the absolute speed limit of the universe, light still isn't fast enough. It can't keep up with the expansion of space. It can't reach every corner of the cosmos. It can't connect us to distant galaxies that are already receding faster than light can travel. There are stars being born right now whose light will never reach Earth. There are civilizations that might exist, or might have existed, whose signals will never cross the gulf of space to touch us. This is the paradox at the heart of cosmology. The universe is governed by strict laws, precise equations, unbreakable limits. And yet those same laws create boundaries that we can never cross, horizons we can never see beyond, mysteries we can never solve. The faster the universe expands, the more of it becomes unreachable. The more we learn, the more we realize how much we'll never know. But I want to leave you with a different thought. Yes, there are limits. Yes, there are things we'll never see, places we'll never go, questions we'll never answer. But consider what we have accomplished in just the last century. In 1920, we didn't know other galaxies existed. In 1998, we didn't know the universe's expansion was accelerating. In 2015, we hadn't detected gravitational waves. In 2019, we hadn't imaged a black hole. In 2022, we hadn't seen the first galaxies forming in the early universe. Every generation discovers something that the previous generation thought was impossible. We've gone from thinking the Milky Way was the entire universe to mapping the cosmic web across billions of light years. We've gone from Newton's clockwork universe to Einstein's curved space-time to quantum fields and dark energy. We've gone from looking at the sky with our naked eyes to building telescopes in space that can see the universe as it was just a few 100 million years after the Big Bang. And we're just getting started. The next generation of telescopes is already being built. The extremely large telescope in Chile, with its 128-foot mirror, will be able to image the atmospheres of exoplanets and study the first stars in unprecedented detail. The Nancy Grace Roman Space Telescope will survey vast areas of the sky, mapping dark matter and searching for planets around other stars. The Square Kilometre Array, a radio telescope spread across thousands of kilometers, will probe the cosmic dark ages and study the evolution of galaxies. We're developing new technologies, quantum sensors that can detect gravitational waves with incredible precision, neutrino telescopes that can see through the entire Earth, cosmic ray detectors that can study the most energetic particles in the universe. We're using artificial intelligence to analyze data, finding patterns that human astronomers might never notice. We're collaborating across borders, across disciplines, across generations, all working toward the same goal, understanding our place in the cosmos, and perhaps most importantly, we're asking better questions. We're not just asking what the universe is made of, we're asking why it's made that way. We're not just measuring the expansion rate, we're trying to understand what's driving it. We're not just searching for life, we're thinking about what forms life might take, how it might communicate, what it might teach us about ourselves. The universe is vast and ancient and strange. It operates on scales that dwarf human comprehension. from the infinitesimal quantum foam to the cosmic web spanning billions of light years. It contains phenomena so extreme they seem impossible. Black holes where gravity is so strong that not even light can escape. Neutron stars where a teaspoon of matter weighs as much as a mountain. Quasars that outshine entire galaxies. And yet somehow we understand it. Somehow, through mathematics and observation, through theory and experiment, through creativity and persistence, we've figured out the basic rules. We know that the universe began in a Big Bang. We know it's been expanding for 13.8 billion years. We know it's filled with dark matter and dark energy. We know that stars forge heavy elements, that galaxies evolve and merge, that space-time can ripple and bend. We've done all of this from one small planet, using instruments that are little more than sophisticated light buckets and particle counters. We've never left our solar system. No human has traveled farther than the moon, and yet we can see and measure and understand things that are billions of light years away. That's extraordinary. That's something to celebrate. Yes, the fastest thing in the universe isn't fast enough to reach every corner of the cosmos. Yes, there are fundamental limits to what we can observe and where we can go, but those limits don't diminish what we've achieved. If anything, they make it more impressive. We're working within constraints, the finite speed of light, the expansion of space, the laws of physics, and we're still making progress. We're still learning, we're still discovering, and we're doing it together. Every telescope, every detector, every satellite is the product of thousands of people working in concert, engineers and technicians, scientists and mathematicians, programmers and administrators. Every discovery is built on the work of previous generations, standing on the shoulders of giants. Every question we answer opens up new questions, creating opportunities for future researchers to make their mark. This is the human adventure. This is what makes us special. We're made of stardust, yes, but we're stardust that can wonder about its origins. We're the universe observing itself, asking questions, seeking answers. And even though there are limits to what we can know, even though there are horizons we can never cross, the fact that we can understand those limits is itself a kind of triumph. So the next time you look up at the night sky, remember what you're seeing. You're looking at the past. You're seeing photons that have traveled for years, centuries, millennia, eons to reach your eyes. You're seeing the universe as it was, not as it is. You're witnessing the great cosmic dance of expansion and evolution, of creation and destruction, of matter and energy transforming across billions of years. And remember that you're part of it. The calcium in your bones, the iron in your blood, the carbon in your cells, all of it was forged in the heart of a star. You are made of the universe, and the universe is made of you. The boundary between you and the cosmos is an illusion. We're all connected, all participants in the greatest story ever told. The fastest thing in the universe isn't fast enough to outrun the expansion of space, but it's fast enough to bring us messages from the distant past. It's fast enough to show us wonders we never imagined. It's fast enough to inspire us to keep searching, keep questioning, keep reaching for the stars. And that, I think, is enough. Light may not be able to reach every corner of the universe, but it can illuminate our minds, expand our horizons, and remind us that we're part of something far greater than ourselves. In a universe that's constantly expanding, constantly changing, constantly moving beyond our reach, light connects us to the cosmos. It's our window into the infinite, our bridge to the stars, our link to the very beginning of time. So yes, the fastest thing in the universe isn't fast enough, but it's given us everything we know about the cosmos. It's shown us where we came from, how we got here, and where we're going. It's revealed the beauty and complexity of nature, the elegance of physical laws, the profound interconnectedness of all things. And for that, we should be grateful. Because even though we can't see everything, even though we can't go everywhere, even though there are questions we may never answer, we can still look up at the sky and feel connected to something vast and ancient and wonderful. We can still ask why. We can still seek truth. We can still marvel at the mystery. That's the real gift light has given us. Not just information, but inspiration. Not just data, but wonder. Not just answers, but better questions. The universe is expanding. Galaxies are receding. The cosmic horizon is shrinking. But our curiosity is limitless. Our imagination is boundless. And our capacity for understanding continues to grow. We may be stuck in one small corner of an unimaginably vast cosmos, but our minds can roam freely across space and time, exploring realms that our bodies will never reach. So keep looking up, keep asking questions, keep pushing against the boundaries of knowledge. Because even though the fastest thing in the universe isn't fast enough to show us everything, it's shown us enough to know that the cosmos is far stranger and more beautiful than we ever imagined. And the journey has only just begun. If you want to dive deeper into the practical limits of human space exploration, I highly recommend watching the video at the left side of the screen. This is why we are stuck in the solar system forever. In that video, we explore the enormous challenges facing interstellar travel, the engineering obstacles we'd need to overcome, and why reaching even our nearest stellar neighbors might remain forever beyond our grasp. See you there.